Comprehensive analysis of hypothetical silver recovery system. Abstract. This report evaluates the efficacy of a multi-step hypothetical system designed for the recovery of silver from aged and heavily patinated silver-plated flatware. The system relies on a sequence of chemical reactions involving cyanuric acid, sodium percarbonate, oxalic acid, sodium hypochlorite, hydrochloric acid, calcium carbonate, sulfamic acid, and sodium hydroxide. Each step is analyzed based on stoichiometric probabilities and chemical principles, while also considering potential errors, plus 30 degrees from optimal conditions, and the compact space-constrained setup. Step-by-step analysis. Step 1. Cyanuric acid and sodium. Percarbonate, bath and table vinegar. Reaction overview. Cyanuric acid acts as a mild chelating agent, potentially binding with surface oxides or patina on the silver-plated items. Sodium percarbonate, Na2CO3, bond 5H2O2, when dissolved, releases hydrogen peroxide, H2O2, and sodium carbonate, then A2CO3. Creating an oxidizing environment. Table vinegar, acetic acid, CH3COOH, provides an acidic medium to dissolve surface oxides and patina, e.g., silver sulfide, Ag2S, and react with carbonate ions to release CO2 gas. Reactions. Down to 1. Sodium percarbonate. Decomposition. Na2CO3 1.55H2. O2, Na2CO3, plus 1.5H2O2, oxidation of silver sulfide, Ag2S, plus 4H2O2, 2Ag. plus LO42 plus 48H2O3. Acetic acid reaction with sodium carbonate Na2CO3 plus 2CHCO OH 2CH3 CoNi plus CO2 plus H2O. Advantages: effective at oxidizing surface tarnish, Ag2S, and exposing silver. Produces a mildly alkaline environment, from carbonate to stabilized silver ions. Disadvantages: excess peroxide decomposition may lead to loss of oxidizing potential. The reaction may generate unwanted sodium acetate. Which could accumulate over multiple cycles. Likely solution contents: post-step 1, sodium acetate, CH3-CuE8, dissolve silver ions, Ag+, sulfate ions, SO4. Residual cyanuric acid and hydrogen peroxide. Trace CO2 gas release. Step 2. Introduction of oxalic acid and sodium hypochlorite reaction overview. Oxalic acid. H2C2O4. Reducing agent, capable of precipitating silver ions as insoluble silver oxalate, Ag2C2O4, sodium, hypochlorite, NaClO, oxidizing agent, which can oxidize remaining contaminant. Or organic residues. Reactions: 1. Precipitation of silver oxalate. 2Ag plus H2C2O4. Ag2C2O4 plus 2H. Hypochlorite, oxidation, optional. NaClO plus H2O HOCl plus Na plus OH. HOCl oxidizes organic impurities or remaining sulfides. Advantages: efficient silver recovery as silver oxalate. Hypochlorite may help clean contaminants and stabilize the solution. Disadvantages: oxalic acid could lower solution pH. Too much, requiring careful control. Unreacted hypochlorite may degrade oxalates or produce unwanted byproducts. Likely solution contents. Post-step 2. Precipitated silver oxalate, Ag2C2O4. Residual sodium ions, Na+, hypochlorite, and oxalates. Carbon dioxide, CO2, gas from oxalic acid decomposition. Step 3. Introduction of hydrochloric acid. Dilute 30%. And calcium carbonate. Reaction overview. Hydrochloric acid, HCl. Dissolves silver oxalate, converting it to silver chloride, AgCl, an insoluble. Precipitate. Calcium carbonate, KaCO3, neutralizes excess acid and prevents overacidification. Reactions. 1. Conversion of silver oxalate to silver chloride. Ag2T2O4. Plus 2HCl, 2AgCl, plus H2C2O4. 2. Neutralization of excess, HCl, CaCO3, plus 2HCl. CaCl2 plus CO2 plus H2O. Advantages. Silver chloride is highly insoluble and easy to isolate. Calcium carbonate ensures pH remains manageable. Disadvantages. Calcium chloride, CaCl2. In solution may interfere with subsequent reactions. Overuse of HCl could lead to loss of silver ions as soluble Ag+ complexes. Likely, solution contents. Step 3. Precipitated silver chloride, AgCl, dissolved calcium chloride, CaCl2, carbon dioxide, CO2, gas. Step 4. Introduction of sulfamic acid, sodium percarbonate, sodium hydroxide. Reaction overview. Sulfamic acid. NH2SO3H. Used to dissolve any remaining scale or metal oxides while suppressing nitrous oxides. Sodium percarbonate and sodium hydroxide. Strong oxidizing and alkaline agents to further purify silver. Reactions. 1. Metal oxide dissolution by sulfamic acid, MO, plus NH2SO3H, MSO3, plus H2O, plus NH4 plus, M=12 metal. 2. Oxidation of residual metal contaminants. Na2CO3, 1.5H2O2 plus M. M2 plus CO32 plus H2O. Advantages. Cleanses remaining impurities and exposes pure silver. Strong oxidizing and alkaline conditions promote purity. Disadvantages. High alkalinity may degrade sulfamic acid prematurely. Excessive oxidation. Could dissolve some silver. Likely solution contents post-step 4. Dissolved metal sulfates, sulfamates. Residual silver precipitates, AgCl or Ag2O. Steps 5, 8. Precipitate separation and recovery. Key processes. Step 5. Remaining metal, e.g. copper or base metals, is segregated into a recovery bucket. Step 6. Solution is decanted into new jars retaining active compounds for reuse. Step 7. Fresh hydrochloric acid is introduced to separate copper precipitates from white-gray silver precipitates. Step Copper is discarded while silver-rich precipitates, AgCl, Ag2C2O4, are retained. Advantages: effective separation of silver from base metals. Solution reuse minimizes waste and enhances concentration. Disadvantages: losses may occur during decanting or due to incomplete precipitation. Copper may interfere with silver recovery if not fully separated. Overall efficacy: this system shows promise for recovering silver from heavily patinated flatware, especially in a space-constrained setup. The use of strong oxidizers, acids, and selective precipitating agents ensures efficient recovery. Though careful control of pH, concentrations, and reaction times is critical. Errors: bust out in 30 degrees, and higher concentrations are tolerable but may reduce yield or purity. Final notes: solution ready for reuse, step 6. Likely contains sodium acetate, calcium chloride, and residual oxygen. Oxidizing agents, making it suitable for further silver plate processing. Recovered precipitants, Step 8. Silver chloride, AgCl, and silver oxalate, Ag2C2O4, are the primary silver-containing compounds ready for further refining. This process balances efficiency and compactness, making it suitable for microlab setups, though further refinement could improve yields and reduce byproduct accumulation.